In this lesson, we cover the basics of infrared or IR spectroscopy. So when molecules absorb infrared radiation, the bonds vibrate. So what are some examples of vibrations? You could have the bonds stretching. You can have the bonds bending in plane, which is called scissoring, up and down. Or you can have the molecule bend out of plane, in which you're having it twist back and forth. So when you do an IR experiment, the output that you get is called an IR spectrum, and it is a plot of percent transmittance versus wave number. Okay, so we'll talk about what both of these concepts are. So in any spectrometer, you have the source of the radiation, you have the sample, and you have the detector. So if you had no sample there, light would be going from the source straight to the detector, and all of it would be transmitted. If you put a sample in between the source and the detector, the sample is absorbing light at certain frequencies. And the frequencies of light that get absorbed, of course, are not reaching the detector and not getting transmitted. IR is the only common spectrum where we report percent transmittance rather than absorption of light. But because we report percent transmittance, the peaks are negative. Okay, so in the example given here, we are getting radiation at 3400 wave numbers being absorbed. So that represents low percent transmittance, and the baseline is at the top. So for example, at 1900, there is nothing being absorbed, so all of it is being transmitted, and you see a line at the top. All right, so then what is this crazy thing called wave numbers? Well, wave numbers are, and then the units of it are centimeters to the -1, which we also call reciprocal centimeters. Wave numbers are the number of wave peaks per centimeter. So if you think about this in the context of water waves, as you go to the beach, you could be thinking, how many wave crests are there in 100 meters? And if you measure how many water wave crests there are in 100 meters, you'll get a reasonable number of them, 10 maybe. I don't know, it depends on how windy of a day it is. So water waves have fairly large wavelengths, the distance between the top of one wave and the top of another wave on the order of a meter. But infrared waves are much, much closer together. Their wavelength is on the order of micrometers rather than meters. So the distance unit that we use to get a reasonable number of waves in that distance is the centimeter. So if you look at the spectrum here, the left-hand side are places where the frequency is 4,000 waves per centimeter, and then on the right side, there's only 400 waves per centimeter. Okay, so this is a factor of 10 difference in frequency from the left side to the right side of the infrared spectrum. Okay, wave numbers are sometimes given the Greek letter nu with a line over the top of it, and wave number can be calculated simply by taking the reciprocal of the wavelength, 1 over the wavelength, where in this case, lambda is going to be the wavelength in centimeters. Okay, so which side has higher energies and which side has lower energies? Well, E equals h nu is the fundamental equation of spectroscopy, but when we apply that to wave numbers instead of frequencies in hertz, we need to multiply by the speed of light. So E equals hc nu. The important thing here is that energy is directly proportional to wave number. So what that means is that peaks at higher wave number on the left side of the infrared spectrum represent higher energy vibrations. Okay, so that's all well and good. Well, what kinds of stretches would we expect in what region of the spectrum? Okay, so this is our roadmap, so to speak, of how to interpret an IR spectrum. So the center of the spectrum is roughly 1,500 wave numbers. The region to the left of 1,500, if you look at the spectrum, let's just go back and look at the spectrum. The region to the left of 1,500 actually contains relatively few peaks. The region to the right of 1,500 contains a lot of peaks. Okay, so all you find to the left of 1,500 in the higher energy region are stretches of multiple bonds and bonds to hydrogen. Okay, so specifically 3,000 to 3,600 or so is where bonds to hydrogen stretch, so carbon, hydrogen, oxygen, hydrogen, nitrogen, hydrogen bonds. And the way to think about that, think about a hydrogen as being like a marble that's bound by a spring to a very large ball, like a basketball. If you were to take a marble and pluck and extend that spring and pluck it off the basketball, it's going to move back and forth really, really fast at a high frequency because it's so light compared to the big ball. Big ball's hardly going to move at all. The same way, bonds between carbon and hydrogen or other elements in hydrogen will also vibrate relatively quickly, and they vibrate at high frequency, so they absorb higher frequency light. Then, in terms of carbon-carbon stretches, triple bonds are stronger than double bonds, which are stronger than single bonds. So it takes more energy, higher frequency of IR radiation, to stretch a triple bond than it does to stretch a double bond, which subsequently has more energy than is required to stretch a single bond. So most functional groups have either multiple bonds or bonds to hydrogen as being characteristic of that functional group. Think about it. Carbonyl has CO double bonds, alkenes, aromatics have CC double bonds, alkynes, nitriles have triple bonds, alcohols have OHs, etc. So that's why this region of the spectrum is called the diagnostic region, because you can tell what functional groups are present based on whether a stretch at that particular frequency is present. And in the next lesson, we'll go functional group by functional group and look at exactly, take a finer, zoom in and take a finer look of exactly where we would expect a peak to be for a certain functional group. Right now, we're still looking big picture. The region below 1,500, as we saw, contains many peaks, and this is the region due to single bond stretches as well as all kinds of bends. Now, every compound has a unique set of peaks in this region, but of course every compound has lots of single bonds. Lots of carbon-carbon single bonds or carbon-oxygen if they're present. So this region is not that useful for diagnosing which functional groups are present in a molecule, but it has a different use. It is called the fingerprint region because every molecule, even if they are very similar structurally, is going to look different in the fingerprint region. So looking at the fingerprint region can unambiguously identify a compound. Okay, so depicted on the bottom here are the spectra of 2-propanol and 2-butanol. The only difference between these molecules structurally is the presence of an extra CH2. And if you look at the two spectra, they are virtually identical to the left of 1,500, but they look quite different below 1,500. So part of quality control at, for example, pharmaceutical manufacturers is they run IR spectra of each batch that they make of a drug. They run other types of spectra also, but one of the important quality control tests is to run IR spectra, and they have to match exactly. If there is any difference in the IR spectrum, that could be indicative of some impurities present. Okay, so in the next lesson, as promised, we will zoom in and look at exactly where to find stretches for the different functional